Okay, so basically, I think ND is ND is an application area, and so we'll talk about a lot of it. At least I know where to pitch it, what level to pitch, and so on. Okay, before we start, I'll just introduce a little bit from about where I'm coming from. So you can see that this is the state of Michigan, and if you look at Michigan itself, the capital of Michigan is Lansing. It doesn't even show Lansing. So Lansing is such a small town, and although. Oh yeah. I was looking at the wrong place. There, this is Lansing over here. Couldn't find. And Michigan State is in a city called East Lansing. It's about 3.5 miles east of Lansing. Okay, and so, and this greater Lansing area has a population of about 400,000. So, now of course, the more the city in Michigan that everybody knows about is Detroit, and that is over here. That's where all the automotive industry took off in a big way and still continues to do that. So, and Detroit is about 84 miles from Lansing, and the other big city is in the west side, which is Grand Rapids over here, which is really big in insurance and medical and those kind of industries. And we are also right at the border of Canada. So in fact, they say Windsor, which is on this end, is to the south of Detroit, actually a little bit. So anyway, the other thing about Michigan, the state of Michigan, is the Great Lakes. We have the largest body of freshwater lakes. We have Lake Michigan, Lake Huron, Lake Erie, and Lake Superior, and Lake Ontario. So there are 5 Great Lakes over there. And these are some simple facts about my department. We are about 42 faculty, and actually in the process of hiring at least 10 more very soon. We also have some research or teaching faculty, which are the instructors who basically help with teaching. And we have 10 support staff and then we have about graduate students, 220 graduate students. 30% of these students are masters, and about 70% are PhD students. So we focus a lot on PhD production, because the ranking in the US, the ranking of a department or a university depends on number of PhD students, the number of publications, and so on. And since PhD students are more interested in publications, every faculty member, they tend to hire only PhD students. So if you send an application letter and say you're interested in doing a master's, faculty will not even admit you. And the way, the application and review process is quite different over there. It's up to the individual faculty to either admit to, eventually, once there is a review committee which says these students are admissible, that they follow other criteria, then unless there is a faculty member willing to take the student on as a PhD student, they don't get, even if you're admissible, you may not get admitted, because every student is admitted with the financial support. And if there is no faculty member with the financial support, then the student cannot get admitted, not eventually admitted. And we have about 800, which I think, this is a slightly old statistic. I was just telling this morning, during this pandemic years, the enrollment has gone up. We are now about 1,200. This number is now about 1,200. Okay. And these are some of the areas of specialization. We group them into 3 different areas: electroscience, systems, and computer engineering. So ours is electrical and computer engineering. So we have, in the area of electroscience, we have materials and device, electromagnetic, and non-destructive evaluation falls in this. Although I think non-destructive evaluation also falls in the systems area. So we have all this communication, signal processing, power systems, controls, robotics, and biomedical systems fall in the systems area. And then, of course, we have the computer engineering as the other area of specialization. So that sort of gives you an idea of the department itself and the kind of work that goes on over there. Although in the recent years we have other areas that have developed. Autonomous vehicles is another big area that's taking over. In fact, in Michigan State University, I don't have a picture of that over here. If you go to the website, you can see there is a bus which is fully autonomous that will be just driving around the campus, transporting students from a parking lot which is outside the campus to the heart of the campus. So I think, Michigan State being very big in automotives and transportation, and all countries are now moving towards autonomous vehicles, driverless vehicles. That's another area, up and coming area. In fact, the state of Michigan wants to start an electric vehicle academy, which will train students in those focus areas for electric vehicles. It has both electric vehicles, which is a lot of battery science, and then autonomous driving, which is a lot of control system, which is a lot of image processing, real time, and sensors. These autonomous vehicles have about 20, 25 sensors all around, giving all kinds of information that's used. Okay, so that's about Michigan and Michigan State. So let's stop this, and I will. We'll start with the GIAN lecture. Okay, so what I have planned today is to give you an overview of how these courses are organized over the next 2 weeks. Okay, so I'm just going to give you an overview. We'll talk about, this is a roadmap. We'll talk about what is an NDE system and some example of NDE projects that we have done, gives you a better feel, and the different types of NDE methods, and some examples again. Okay, so what is non-destructive evaluation? I think Professor Rao described this morning that it's a science of evaluating structural integrity of a material without breaking it apart. I think the simplest example is biomedical imaging. So if you have a fracture in your bone, you don't have to cut open to see. You just do an X-ray, which is non-invasive, and look at the image. You see the fracture, and you determine what needs to be done next. So it's the same thing with other materials. For example, these are some pictures of Aloha Airlines in 1981. Aloha Airlines used to fly between all the different Hawaiian airlines. And because of the humidity in the islands, there was a lot of corrosion. And if you look at an aircraft fuselage, it consists of thin aluminum layers which are all riveted together, right? 2, sometimes 3 layers. There are stiffeners. It has a complex structure, but these are all riveted. And very often, it is the in between the layers which corrodes. And then, so the defect sort of starts at the rivet sides. That's a high stress region. Starts joining. They become a big, long defect. And when this airplane was landing, this whole top just flew away because it was a long crack. It's called a multi-site damage. And so if we had good NDE methods, we could have detected this at an early stage before it became so dangerous. So this is the same thing. So after this, the Federal Aviation Administration started a big program on aging aircraft. In fact, I think 2019, there was a government-funded program called Vaibhav in Madras, which IIT Madras initiated that, led the program. but they invited again people from all over the world to share their experiences with NDE of aging aircraft and see what's the best practices, because as I said, these are all global problems. Every country is facing these. They all fly airplanes. We all have problems. So it's nice to share. We don't have to reinvent the wheel. We need to know what others are doing so we can come up with a good method. And here is another example. Here is where an entire bridge collapsed. A bridge contains a lot of steel structures which can corrode. And if they are not inspected and cracks are not detected on time, you can have the whole thing collapse. And here is an example of a railroad, and this is a pipeline. In the US, there's about 1 million miles of buried pipelines, all of them carrying highly inflammable gas under very high pressure. And if we don't detect corrosion of these pipelines, you can have the whole pipeline explodes. And this goes through residential areas, or sometimes apartments can go on. And of course, space program, you have a lot of parts that needs to be detected, or the cracks need to be detected. So basically, that's the motivation why NDE has become a big part of industrial growth. And here's an example of, this is a nuclear plow. These are all examples of NDE funded activities in my group. The nuclear program, there's a space, NASA funds much of our research. The Navy has given us funding for looking for cracks in submarine hulls, biomedical, and this is the aviation. And this example is implanted heart valve. You look at many people, there's thousands of people have implanted artificial heart valves. These are made of metals, and blood is very rich in oxygen, so very corrosive. So you want to detect, of course, non-invasively, any corrosion in implanted heart valves. So those are some motivational slides for why do we need to do NDE. So this picture is generic NDE system. All NDE systems, they have some kind of excitation source. And this can be electromagnetic, ultrasonic. In biomedical, we do a lot of ultrasound, we do MRI and radiography, X-ray, and we can have an optical NDE method. So with this sensor or the input transducer is a big area of research. So the energy interacts with this material, which may have a flaw. This sample can be an aircraft, it can be a part of a power plant, or the rails and pipelines, many of these things. Or it can be as a small IC chip. You want to look for connectivity of all the carbon lines. So there is this crack. So, it spans the entire gamut. And then you pick up, this interaction produces a response signal. You pick that up with a measurement transducer. And then this signal that has to be interpreted. So you do some image processing, signal processing to condition these signals, basically remove noise and remove irrelevant information. We'll come to more details about it over the next 2 weeks. And then it goes to the inverse problem. Okay, this is inversion. And so you take this signal, you interpret. What is inversion? You get the signal, you measure the signal, and from this measurement, you want to know the image of this flaw, right? And from that, once you know an accurate estimate of the flaw, you can use a structural mechanics model and see whether is it going to fail. Can this airplane fly once more, or should it be grounded? And then you can determine what is the remaining useful life of that structure. It's called RUL. So this is a generic NDE system. So all the research, everything is related to one of the components, and I'll talk about that next. Okay, again, one thing is, let's keep this very informal. If there's anything you want to ask, you can stop me and we can discuss, okay? So there are, as I said, depending on the sample, the material of this sample could be conducting, it could be steel. Yes.
So one interesting question or I'm curious, generic ND kind of DUTs or those samples here.
Yes.
Exactly how submarines would say that
That's correct.
it's a big things are there.
Right. Right. Yeah, very good question, really. I'm glad you brought this up before I went. You know, ND, these are that's why I call it generic. These are the common thing. But the problem with NDE, one of the things that's required is depending on the application, whether it's a submarine or an aircraft, the NDE engineer has to determine what kind of sensor, what should be scanned, how do you interpret, the interpretation algorithms are going to be entirely different from application to application. So that is why, even though there are many commercial systems available, it doesn't solve the problem because you need someone with a better understanding of how to interpret the signal that you have. And I'll show some examples. And I think that's one thing. I'll talk about this in generality, but unless you look at an actual system, it's very difficult to get an appreciation for what kind of challenges are involved in these systems. Yeah, thank you. Yeah. So again, today I will just give an overview, and then over a period of time, when you talk about magnetic ND, we'll talk about specifics. And when you talk about, unfortunately, we're not doing ultrasonic in this, it's only electromagnetic method. But I will, in the signal processing side, we will talk a little bit about those also, which, okay. Okay, so these are the different classes. We have visual methods. This is the earliest of the NDE methods. Ultrasonics, again, is probably one of the most commonly used method. If you go to an NDE conference, we have an annual conference in the US on NDE for 5 days, Monday to Friday, but you will see that 3 of the days will be just focusing on ultrasound. And all other methods take the remaining 2 days, so the fewer sessions, because ultrasound is very versatile, and there is no restrictions on the type of material, whereas electromagnetic, there are restrictions, as we'll see. Okay, and of course radiography, and then you have infrared thermography. I believe there is infrared thermography work going on in IT. And of course, electromagnetic method. These are some of the commonly used NDE methods. Okay, let's just go over very, very briefly how does these generic systems look like? No longer generic, the different NDE system with different kinds of sources look like. Again, the earliest method, if you go to in the early 20s or early 20th century, it was all visual. Dye penetrant is a visual method. So basically, you do clean the thing and you pour some a dye, which if there are surface cracks or near surface crack, it sort of goes inside, and then you use an ultraviolet light to illuminate that particular dye. So that is a pretty basic, pretty primitive method. Okay, so it takes fluorescent liquid, which goes into the surface cracks, but they were used in rails and pressure vessels in the power plants. The cladding in the pressure vessels were all detected. Those cracks were detected using dye penetrant. But again, it can only do the surface cracks. And very often, cracks can be below the surface, and we'll see that later. Mac particle was a little bit of an improvement. So these liquid are also has a lot of ferromagnetic particles. So what you do in this is, it's a two-step method. You first magnetize the specimen. So immediately, if you have to magnetize, the sample has to be magnetic. You cannot magnetize aluminum, right? So for aluminum, you use dye penetrant. For rail heads, you can magnetize it. the rails which are, so then you magnetize it. So then what happens is there's a little local field near the cracks. And then when you again pour these liquids with the ferromagnetic material, those particles get attracted by the magnetic field and then they'll stick to the crack. And then once again, you use some kind of ultraviolet light and pick up those magnetic particles. So these are pretty primitive. Things have gone a long way. If you have to go through 100 miles of rails and do this for, locally, it's going to take you a couple of years to inspect. So that's not what you want to do. Okay, ultrasonic method basically involves, if you look at this is the, can you see my, oh, you can't see my, this is the way, oh, how do I get the cursor to show? Is it this one? Ah. Okay, so this is your input transducer. So it's an ultrasonic transducer. You can launch an ultrasonic wave. It goes to the back wall, and then it gets reflected. So ultrasonic waves, whenever there's a mismatch in impedance, it will reflect, right? So it goes through this thick sample, and then it gets reflected, and then you can look at, so the signal would look like this. This is the top surface signal, and this is the reflection from the back wave, back wall. And if there is a crack in the middle, you'll have the front wall, the crack wall, and the back wall. So that's a simple way of getting ultrasonic NDE signal. So this particular modality where you have the same transducer which produces the input as well as the receive is called the pitch catch. Sorry, it's called the pulse echo. You're just getting the echo. And over here, you have the input wave comes from here. And if there is a crack, it's diffracted. It's picked up by another transducer. It's called the pitch catch. So this pitches and this transducer will catch. And the signal from here may look like this. So from the geometry of your sample and simple ray diagram, you can sort of know what your signal is going to look like. And so you can have the front wall, then you have the crack, this is the top surface diffraction and the bottom of the crack diffraction. So it's much more complex. So let me, yeah, so for the weld inspection, if you look at the submarines, for example, the submarines are made of 2-inch thick steel, and you cannot build entire submarines of one material, right? They take 2 feet by 2 feet sections and weld them together. So there's a miles of welding that needs to be inspected. Welding in the heat affected zone of the welding is where cracks develop. So a lot of weld has to be inspected. So we use typically a pitch catch method. What we show here though is a pulse echo. The same transducer goes in, and some things get reflected depending on the angle of your cracks, and you get signals like this. Now, just looking at one signal individually is very difficult to interpret. If you take an entire measurement and you get an A scan, bunch of A scans. So basically the transducer is moving this way, and each A scan is all plotted one by together, you get an image. And if you have a crack in this fashion, you know that particular reflection, is will produce a feature in the image corresponding to the crack. Okay, so ultrasonic NDE is very versatile because waves can travel, say, up to 2 inches of steel and come back. They bring back more information. Okay, but it's a contact method. How do you couple an ultrasonic wave that is produced in air into the steel? Whenever there is a mismatch in mechanical impedance, there's a lot of reflection. So you need a couplant. And that makes things very slow, and there can also be a lot of variability. The couplant is not the same in this location, and this location produces its own various signals. So it's useful for very thick samples, but there is still, those are some of the advantages and disadvantages. So this is actually, I'm going to talk about this a little later. This is the welding. Yes, oh, sure. It's called contact method because the transducer has to be in contact. Ideally, you would like the sample is here and then just scan without, you can scan so fast if you don't have to have contact. You have to now, if you've been to a hospital and done an ultrasound image, you know that they put a gel and there is the transducer has to go through the gel and couple to the human tissue. It's the same thing in any sample, any metal. So basically, you want the impedance of the two medium. If it is completely discontinuous, you know that it will completely reflect out the same thing is true in microwaves too. So the impedance matching, that's why any instrument that you build, you've got to make sure that your impedance is matched. So that's the reason.
Lambda by 4 transmission line.
Yes, exactly. So you have to.
Couplant is to act like that.
Exactly. Yep. Yeah. There are acoustic microscopes which basically use a quarter wavelength coupling medium for very efficient, coupling into the sample. So coupling that's the big disadvantage of ultrasonic ND. But so one way of, what I've talked about here is a contact method. Okay, that's another thing I should point out, which is not there in the slide. Another way of conducting an ultrasonic NDE is to immerse the whole thing in water, in a big tank, in which case the water becomes a coupling medium. I don't need to go and be in contact with the sample. I can just, scan from 2 inches above the sample. But the whole sample has to be immersed. So that's called the immersion method for ultrasound. Yeah, that's a good thing. That's is contact method or immersion method. But again, it's not always convenient to immerse a big. It's probably very convenient for submarines which are already immersed. You don't need to that. But for many samples, it's difficult. So these are, I think, yeah. 0. That's why it's called contact. It has to be in contact with the sample. You have to put the couplant and you have to touch the sample. There's maybe a film of the couplant, very thin. So those are some disadvantages of. There are some gel. I don't have offhand the information, but there are couplant gels. Sometimes glycerine is a good couplant. So it has to be viscous enough to stick, and also the impedance properties have to be right for that particular thing. Okay, so in ultrasound, there are 3 modalities of looking at the data. So this is called the A-scan. It's just put a transducer in one location and look at the time. This is the time axis, and you're looking at the return amplitude. And this is called the B-scan, where you move it along one line, and at each point you plot the A-scan, and when all the A-scans are plotted together, you get this image over here of the crack. And that's what medical ultrasound does, just that. Each ultrasonic transducer has an array of, instead of moving one transducer, you have an array of transducers. And then when you just look at it and you get this whole B image. And then if you can do a full raster scan and plot the max peak value at each point, you get what's called a C scan. So you have A, B, and C scan modalities for looking at an image. So that's ultrasound. There's another method called acoustic emission. And the nice thing about this is it's passive. Every material goes through, whenever it is stressed or loaded, it is subject to some kind of changes in stress levels. And this triggers the release of energy from the grain structures or atomic level structures in the sample. And these will travel to the surface like a shear wave, and then you can pick it up with any ultrasonic transducer. But again, it's, it's very blind. So what we can do, what we have done is you can use multiple pickup sensors, and you also have a timestamp. So then you can use some triangulation to determine where the crack is. But it's very difficult to image a crack accurately because but this is one method. Acoustic is passive versus in ultrasound, you have an interrogating energy form that goes in. And so we have a good control over where the energy is going and what is the pickup signal, where is it coming from, and we can interpret better. If I just put a sensor here and there's a crack there or there, which produces a signal. Every crack, or not really a crack, these are microscopic level. There is at the crystal structure of the material, if there's a dislocation and very, very initial stages of stress, there is a release of energy from somewhere, and it will travel to the surface because it is sound, but it is at the acoustic frequencies, much lower sound, lower frequency sound, and you can pick up that. There's no incidence energy. It's created by itself. See, any material, you suppose you take a material and keep on flexing it. Okay, so the energy is released in the, so any piece of equipment due to vibration. Okay, there is some kind of a weakening, fatiguing. When there's a fatiguing of the material, it will inherently release this. That's what the processes that release the energy is at atomic level or crystal structure level of the material, or what I call microscopic level. Yes, so typically it's not that commonly used because it's very blind. We don't have any control over what is happening. People probably usually do this what's the pencil tip experiments. We did some work on we can get acoustic sensors or ultrasonic sensors that are very, very small, PVDF films. So we can have wireless sensors, and we can mount my wireless sensors. These are all just passive. And when there is a crack released somewhere, all of them will hear something. And we also timestamp those occurrences. We can use triangulation and determine, oh, this crack, this signal came from here because this would have reached here at this time. That. So we have done some work in that, but we really don't have much control over what we are inspecting and where the signal is coming from. Where should I put my sensors? If I'm putting my sensors here and it is somewhere there, it may die out before it comes here. But nevertheless, it is a good method. If you can embed these continuously and monitor, possible. Particularly in aircraft engines, there are so many parts in aircraft which are cyclically loaded, right? That's what causes fatigue, and acoustic emission testing can be used. But it's basically the interpretation algorithms have to be very complex. And also, acoustic emission, because we don't have an idea of the geometry of the source, and it can have reflection. You get the signal, you have reflection. So the signal, if you've seen it, looks extremely noisy. The crack signal may be embedded in a lot of noise. So interpretation is a problem in this answer. Okay. So that, nevertheless, it's a method. Yes. Yes, you have to use only, ultrasonic for non-metallic. Yep. And we have done a lot of work on that. Although I'm not going to talk about that, I'm going to focusing on electromagnetic, but you have thick structures, composite structures. Ultrasonic is again, it can be used, but it's also quite, if you look at a composite structure, you have fibers going in all directions. So there is no, it's not like a homogeneous material where ultrasonic, I know it goes like this and comes back. So there can be, their interpretation again is different. In fact, in the 90s, when composites first came, there was this concept called design for inspectability. Everybody understood, oh, composites are lightweight, they're stronger, they don't corrode. It was very popular to be used, but if there was a crack, it was very difficult to detect. So design for inspectability was one concept that sort of prevented from composites to taking off in the beginning. But now we can embed sensors along the fibers. We have doing some work in fiber optic sensors, which can be embedded along with the carbon fibers and continuously monitor. So technology develops, and then you can do all this. But ultrasound can be used, but as long as we understand all the risk constraints and interpret the signal based on that, we can use it. Pardon? Material density is very important, isn't it? For ultrasonic denser, it will go, much faster. But you can always, in fact, the latest in ultrasonics is called the air coupled. We talked about contact and coupling. That problem is going away now because there is a new development in the sensor, in the way the sensor is built. Of course, you've got to use much larger power, but you can actually do air coupled ultrasound at say 1 inch distance. That's some of the latest things. So it's there. That's for composites, something that we can use. Yeah, although I don't have any slides on ultrasonic, we have done actually air coupled ultrasound for automotive parts, for actual automotive parts. And these were given to us, was blind. They were Teflon inserts for delamination or disbond. We were able to pick it up from ultrasound. Yeah. So this is a slide on radiography. I think all of us are familiar with X-rays, how they work. And again, originally, the first radiography was a film. So you have to first make sure everybody is vacated because, it's an ionizing radiation. So that's one of the problem with radiography. It's ionizing, it's harmful for humans. Want to make sure everybody's left the place. And you use a film, and then of course you expose it for so much time. You take the film, you develop the film. I mean, it's pretty cumbersome. It's not you scan and you see an image. That's what you'd like to do, and that's where the technology is today. So, but anyway, these are the historical. Even now, though, there are digital radiography. Okay, where the detector is a digital detector, CCD detectors, which is fast. And then you have computer radiography where you have phosphor screen, which immediately shows, okay, you don't have to take it out and develop. So it shows you the real-time digital signal, and you have real-time radiography. And these are flat panel detectors, which will convert the radiographic signal into a electrical signal, and therefore you can do real time. Okay. And of course, computer tomography is you have hundreds of these projection images, and then you compute and reconstruct something in 3D. So that's okay. So what else do I have? Sorry. Oh, that's okay. I'll sit. I feel like I will. Then you have infrared. I think there's work going on in NIT in infrared thermography. These are, all of us are familiar with infrared images. So it's one image, the wavelength in the electromagnetic spectrum. The nice thing about infrared is non-contact, and it produces image data. When you give you an image, it's always easy to interpret. You don't have much, you don't need a whole lot of signal processing. It can detect internal defects, and even thick concrete structures, you can look for cracks in that, and it's non-ionizing, it's rapid. So what is the difficulty? Sometimes when you're looking at infrared imaging of this full board, you don't know the depth where it is. Sometimes you can have images superimposed on each other. And it also depends on the ambient temperature. If you look at it in a hot place or a cold place, things are going to look quite different. And there can be variation in the emissivity of different parts. So if you have a heterogeneous, if you have a single homogeneous slab of steel, there's a crack, no problem. If you have heterogeneous material, each with its different reflectivity, emissivity, then it's be a problem. And it's again very sensitive to a near surface or near surface, but when you go far deep in, it's difficult. And it's pretty slow, actually. Okay, some of the newer methods in NDE is the fiber optic sensor. You're all familiar with you guys are doing optical communication. So you have fiber optic, the core glass and the cladding, the refractive index details, so that the light will always totally internally reflect, goes from transmission to receiving. And how do you use this in sensors? There are different ways. So you have a light source, and you have the measurement source over here, and then the detector over there. So and these detectors, you can measure many parameters of light, like the intensity, the phase of the light, the polarization, wavelength, and all those things, and dispersion. And all these measurements can be then correlated with the structure, the strain. Most of the time, fiber optic sensors have been used for strain measurement. So you place something on a material, and when this bends, at that point, there are the strains changes the properties a little bit, and that can be measured. Okay. And the nice thing about, this is another configuration for optical sensors. You can have the measurement zone is over here. You have a light source, it goes there, and then you pick it up by the detector. So this is a single-ended measurement, and this is over here. You can also, you can have just a fiber, or you can have structures within the optical fiber. You can produce a grating, and gratings are like a frequency tuning. So when the grating is sort of stretched out by the strain, then the frequency changes, and you cannot get those things. So I'm not an expert in fiber optics, so I'm going to gloss over a little bit. So there are different configurations, but it's very nice that you can continuously monitor properties of material. For composites, as you talked about, it's a very attractive method if you can design a sensor. Again, as he said in the, sensor design is an important part of an NDE system, and we'll talk more about it. And so I talked about grating. If I have different type of grating, that means I can tune, each one of these are tuned to a different frequency. And depending on the received signal, I know exactly where the crack is. If it corresponds to the frequency of this or this or this or this, you activate it at multiple frequency and look at the returned signal. So you can also get more information. Okay. Okay, so these are advantages of optical fibers. It's pretty obvious: small size, lightweight. And again, you can't do it at a large distance. It has to be embedded in the sample. So it's very thin, so it can be embedded without any producing. Sometimes you embed sensors, ultrasonic sensors are also, you can get film sensors can be embedded, but that itself becomes a source of stress and starts producing cracks. And fiber optic sensors are immune to electromagnetic interference, so that doesn't need any shielding. And it's very good even for whether it's high temperature or low temperature. And it's chemically inactive also. And you can have distributed sensing capabilities with a single fiber. So it's a lot. I mean, these are all very new developments. I'm sure in the next 5-10 years, a lot more things will happen. And once more people start using, you can resolve all little flaws and everything. Okay, so that's how are we doing? I'm going to do a little bit more and then we'll stop for the morning, okay? So far I looked at all the other type of sensors. This I'm going to go over rather quickly because we will be talking in large detail tomorrow in the next couple of days. Electromagnetic sensors covers the entire frequency spectrum from 0 frequency to terahertz, okay? Some of the very, very low frequency methods are the magnetic flux leakage, okay? See, these methods use permanent magnets or current magnetization. And so it sets up a magnetic field. When there is a defect, some of the flux leaks into the air, and then you pick that up with some kind of a field detector. And then you produce a signal corresponding to the defect. Okay. Again, but the only thing is it's used for inspecting ferromagnetic structure. As I said, this won't work with aluminum, right? Or that is. Okay, so what do we do for aluminum? We use eddy current sensor. Again, it's such a simple method. The underlying physics is very, very simple. The sensor is simply a coil. You excite it with an alternating field. Current sets up an alternating field. That field will then you have to have a conducting sample. It will set up an eddy current inside the sample. Eddy current is always in the opposite direction. If the exciting current is like this, the induced current is in the opposite direction. And so the net flux linkage, there's a flux associated with eddy current. Again, I'll talk more about it, doing it very, very quickly here. So the same coil, if you just scan the surface with this coil, the impedance of the coil will change based on the underlying condition. Okay. And we'll talk about it more deeply. So a simple coil is a nice sensor. There's no contact involved. You can keep it at millimeters, couple of millimeters away, and then get information about the defects. Of course, because of what we call the skin depth, it is sensitive to surface. At most, it can go up to ½ inch depth. So it's ideal for aircraft. Aircraft has each aluminum layer is about ½ inch. So if you have 1, 2, or 3 layers, it can even pick up defects in the second layer. So that's eddy current, which is a low frequency, and then you have microwaves. Of course, because of the same skin depth, microwaves cannot penetrate in metal. So then you have a dielectric sample or composites. Even in composite, the glass composites, carbon composites, carbon is conductive, so microwave is not that effective. Okay, so for it's in principle, physical principle, it's very similar to ultrasound. So you have it's a microwave which goes in, it gets reflected just like an ultrasonic transducer, but there's also scattering, the polarization of the E field, the H field. There are differences. In ultrasonic, you have longitudinal wave, shear wave. It's a different underlying physical phenomena are different, right? So that's again we'll have a whole day on just microwave NDE, so we'll not talk about it here. Time domain reflectometry is another method that's coming up particularly for inspecting. It's used for inspecting cables. If you look at a nuclear power plant, there are miles of cables. Okay, an aircraft, there are hundreds of miles of cables going from the front to the back, and so many different cables, and you want to make sure that the insulation is intact. So for such things, we can use time domain reflectometries. It's basically like ultrasound. You launch an electrical pulse, and this pulse travels, and whenever there's a change in the or erosion of this insulation, there'll be some reflection. And so you look at the reflected. Again, it cannot be, it's not used on a large basis, but for some applications, like for cable inspection, nothing else works, but you can't use any other method. And so people are playing around with time domain reflectometry for that. Okay, so that's another method that's used. And anyway, I think I'm going to make all these slides available, and you have the references that talk about these kind of methods. So you'll have. There's another transducer called electromagnetic acoustic. We talked about this came about in the beginning when you have acoustic or ultrasonic method uses couplant. Can we generate ultrasonic wave without couplant? Okay. Before air coupled came about, you can electromagnetically generate an ultrasonic wave. So basically, this is the underlying physical principle is what we call Lorentz force in electromagnetic force. Whenever you have a moving charge and you apply a magnetic field, it's accelerated. There's a Lorentz force that acts on it and all that. So this is based on that. So first what you do is you use a coil and you set up an eddy current. So you have a moving charge or current inside the sample, and then you put another parallel magnetic field, and that will act on the eddy currents. And depending on this is also an alternating field. So the Lorentz force makes it vibrate, and that vibration sets up an acoustic wave or an ultrasonic wave. And then you can then pick it up in the surface. So it's like a fusion of two different underlying physical processes. In this case, we're not trying to even accelerate. You choose the direction of your field, magnetic field, such that you make it really oscillate. So each individual electron charge will accelerate, and that will produce an. I know in cyclotrons and accelerators, they use that in a circular track and for acceleration. Okay, so let me know when I should stop. Okay, and let me see how many slides do I have. I think I have a couple of slides. Then we'll stop for today. Okay, for this morning. So basically, NDE is a very multidisciplinary field. You have to know. In this particular case, electromagnetic, but you also need to know for ultrasonics, you need to know the elastic properties of the material, for the mechanical engineering and electrical engineering. We need to, for depending on the application, you have to design a sensor, okay? There are some generic sensors for ultrasound and for eddy current, but I will show some examples where you take the underlying principles, but you design what kind of coil configuration I've got to use for this particular. Then we have signal and image processing, there's data analysis. You need to know a lot about the material science, and machine learning and pattern recognition is quite, and these are all used in the inverse problem, solving the inverse problem. Okay, very quickly, some of the sample projects for the aerospace industry, we developed an sensor and interpretation for the landing gear, for the wheel inspection, for the holes, rivet hole. This is the impeller bore in an engine, and also in an engine disc, you have these dovetail slots. I don't have all the pictures over here. These are some of the, and I will talk a little bit more when we come to eddy currents, okay? This is another thing. This is where we developed the sensors themselves, okay? It's a coil sensor, but the coil geometry was very different. And this was funded by the Air Force Research Lab. And, we're looking at an inch thick aluminum. And what we have here is a picture of the sample. You have 3 layers, and you have 4 rows of rivets. cracks are typically in the second layer. And so you're looking for, and you want to do it rapidly. You want to have multiple rows to be covered. So we have to have an array of sensors. And I'll talk more about this later on. So this is a schematic. You have 3 layers. Cracks can be in the third layer or the second layer. And then you are scanning from here. You want to pick up something that's embedded defects. Okay. And we used the current, and then this is one example that we did for the Navy for submarine hulls. And in this case, basically the Navy did the signals were all generated by the Navy. And all we did was to interpret the Navy, those signals. And they wanted to know, is it a crack or is it just there is a lack of fusion between the weld material and the steel, or there can be porosity, it can be air bubbles, or it can be slag, some kind of impurity in the weld material. So they were only interested in finding out these different classes of defects, not even to image it. Okay, and because the remaining useful life of that particular weld is dependent on these kind of things. So this, you saw this thing. So we looked at the A scans. We said, okay, let's just look at a lot of A scans and see whether we can see the differences in the A scan from the classes. And then we have a collection of A scans, and we did a lot of work, data analysis work for that. Okay, this shows porosity, for example, will have a different image of the A scan from other. But if you look at these two, one is a crack and another is a volumetric defect. It doesn't look very different. How do I find out? And okay, I just thought a little bit. I'll just talk about the hot weld, the project that we did for Pfizer. So this shows a picture of a hot weld. Basically, a hot weld has a metallic ring. It's called the suture ring, and there is a strut on 2 sides. This is called the inlet strut and the outlet strut. And in between is a carbon diaphragm that beats with each time the heart beats. So each time it heart beats, it sort of beats with a lot of force against this strut. Now these struts are welded. And when they sit in the oxygen-rich blood, they can corrode. And in addition, with the heartbeat, there is additional force on those welds, and we want to detect those kind of cracks. So we basically use an EMAC method. We induce eddy currents in the ring, and then we applied another external field, and we set the whole heart valve into vibration because of. And then you can just use a stethoscope, a digital stethoscope, to look for defects. When there is no crack, the resonant frequency is like 7.5. When there is a crack in that heart valve, the resonant frequency goes to 2.8 or something. So we can just look at a spectrum and determine if there's a crack or no crack. Okay, so these are some of the fields and the direction and the Lorentz force and what is the vibration method, and so on. And this is a schematic of the system. And what we have here is, of course, a single heart valve. Okay. Eventually, we want to do the whole thing with the human being and the valve inside the heart. But this is just to show the feasibility that this method will work. So we have a magnetic field, we have induced eddy currents, and we saw that this is an intact valve, and where the resonant frequency is 7.9 kilohertz, is the intact outlet strut. And this is the broken heart valve. Okay, the last 3 slides. In the US, there is a large NDE activity in NASA, obvious reasons. And of course, much of the cutting edge research in new sensor development, we get funding from. We work with NASA on that. Another place is GE. GE has a very big NDE group, and I think Bangalore has a large NDE group. One of the students from our group was the director of that GM based, Bangalore's based ND activity. They do particularly, since GM is getting into wind turbines, wind energy, wind turbines, they are looking at sensors for composite materials. Some work with them. And Boeing, we have done a lot of work with Boeing. I'll talk about that project. And it's mainly aircraft NDE. But aircraft has so many different parts. The landing gear is one, the engine, the turbine blades, the slots, and everything. So that's my last slide for this morning. I think we all need a break. Yeah, right now. Okay. So we can take a break now, and then what time are we reconvening for? I think so. I think it's a lot of material covered.
The next session start at 2:30. So daily routine will be like phase at 2:30.
Okay, if you want to come by and ask questions, anything about any of the slides, I know I went through some slides quite fast. Feel free to do that. Here, I'll hang around here for some more time.